Hello everyone, and welcome to the Force of Gravity Post Lab. In this lab, you took a bunch of different masses in kilograms and hung them from a spring scale one at a time, and you used the spring scale to measure the force of gravity in newtons. Again, the force of gravity, remember, is an interaction between the Earth and the masses. And then you graphed these force of gravities versus the mass, and you got a nice straight line graph. And not only was it very linear, high correlations, close to 1, if not in some groups, even a 1. It also went through 0, 0. And anytime a graph is linear and contains 0, 0, it tells us something special about the variables. It tells us that the variables are proportional. So we can say here that the force of gravity is proportional to the mass. Now, notice something about that. It doesn't say they're equal. It doesn't say they're the same. Okay? And unfortunately, in common language, people often just interchange mass and force of gravity, or weight, remember, as it's called, and they just use them interchangeably. But what we found in this lab is that they're not equal. You didn't get the same numbers, right, for them, but they are proportional to one another. So if an object has twice as much mass, it has twice the force of gravity acting on it. It weighs twice as much. If it has 3 times as much mass, it weighs 3 times as much. So, of course, being a linear graph, we can create a y equals mx plus b math model out of this. The y variable is the force of gravity, and that equals your slope. Well, you all, of course, entered your slopes into the Google Doc on the website. So let's check out what we have here. Okay, so here we have 34 different values for the slope of the graph of force of gravity versus mass. And you're going to see here, these are all pretty much the same, very close to one another. So if we take an average, we get an average of 9.803. Right, so that's the class average. Now, before we go back to the PowerPoint here, I'm only going to keep the 9.8. And the reason I'm going to do that is because that's kind of where we started to get the variance. Right? If you notice here, all the ones were 9s, in the ones place were all 9s, and it was really the tenths where we started to get some were 7s, some were 9s, some were 8s. So I'm going to kind of round off to just a couple of sig figs here, all right, to 9.8. So I'm going to put in a slope of 9.8. The units for slope come right from how we find slope, rise, which is in units of newtons, over run, which are units of kilograms. Now, what does that slope tell you? Again, remember, this is the slope of a graph of force of gravity versus mass. Well, remember, slopes give you rates of change. They tell you how much one variable changes with a change in the other variable. So, this is saying for every 1 kilogram change in mass, so every time the mass increased by 1 kilogram, the force of gravity went up by 9.8 newtons. So here's the meaning of the slope. For each additional 1 kilogram of mass, the force of gravity increases 9.8 newtons. That 9.8 might be a number you think you might have heard of before, and it is. It's actually a very special number. In fact, it's so special that it's given its very own symbol in physics. 9.8 is given the symbol little g, lowercase g, if you will. 9.8 newtons per kilogram. And in fact, it's given its very own name as well. Little g is what is known as the gravitational field strength. How's that for a mouthful? Near the surface of the Earth. Now, what the heck does that mean? Well, remember that gravity is a long-range force. You don't actually have to be touching the Earth to have an interaction with the Earth. And so, historically speaking, when they were trying to decide how to describe how this force of gravity could work, they decided to come up with a middleman. Basically, it went like this. You have big masses like the Earth. They create gravitational fields around them, right? A force field, if you will. And any mass placed in that field gets a force put on it by the field. So the Earth creates the field acts on other masses. Okay, so it's kind of a middleman. And the field has a strength to it, and this is the strength of the field. The field strength is, for every 1 kilogram of mass, there's 9.8 newtons of force of gravity. So this is why it's called gravitational field strength. It's not gravity. And this is something we're going to go over and over and over again. Little g is not gravity. Gravity is a force. Right? F sub g is gravity. Weight is the force of gravity. Little g is the gravitational field strength. And this is only true, by the way, near the surface of the Earth. If we went and did this lab on the moon, we actually would get the same looking graph. It would be a nice linear graph, but the slope of our graph would only be about 1.6 newtons for every kilogram. Gravity on the moon is about 1/6 as strong. It doesn't create as strong of a field, if you will. Now, I would like you to do a little percent error calculation, as you'll do in class here, to see how far off you are. And please only use the first 2 sig figs like I did. Okay, so don't keep 4 decimal places just because that's what you wrote down. My guess is your experimental is probably going to be 9.8. There might be a few 9.7s or 9.9s, but figure out your percent error so that when you write up the lab, you can talk about sources of error. Now, we need to finish the lab here. Sorry, a little bit behind. So we need to put on the x variable. This is y equals the slope times x. Well, x is what we graphed on the horizontal axis, and that's the mass variable, m. So here we are with the m. The y-intercept, as you can see here, is 0. Right? It goes through 0, 0, and you can check it with the 5% rule. So what does that mean? Well, it means in math class it goes through 0, 0. But what does that physically mean on a graph of force of gravity versus mass? Well, of course, it means that when the mass is 0 kilograms, the force of gravity is 0 kilograms. That should make sense, because if your object has 0 mass, it's not a real object, and therefore it can't interact with the Earth. And so 0 mass is 0 newtons of force of gravity. So that means this is our general, or our specific, math model. And hopefully your slope is what you've written in here at this point. Now, since we know that generally we're supposed to have a 9.8 Newton per kilogram slope, and that is a symbol of a little g, we can plug the little g in and get a more general math model. And you'll notice, too, I flipped the order of these, which is okay because it's multiplication, so it's commutative. So this is traditionally the way you would see the equation. It says the force of gravity acting on an object's weight, is equal to its mass times the gravitational field strength. Remember, little g is not gravity. F of g is gravity. Right? Little g is how much force you get for every kilogram of mass. 9.8 newtons of force for every kilogram of mass. And you'll hear me say this many times throughout the year, F of g is mg. Because this equation allows us to convert from mass to force of gravity, and vice versa. If we divide by g, we can take something's weight and figure out its mass. Again, units are important here. Mass is in kilograms. Force of gravity is in newtons, force units. Gravitational field strength is in newtons per kilogram. If something is in kilograms, you know it's a mass. If something's in newtons, it's a force, or in this case, it's a force of gravity. And again, one other little thing I want to remind you of, as we defined in the pre-lab, weight is a name we can use interchangeably, or a word we can use interchangeably for force of gravity. And so, unlike a lot of the things we're talking about, like mass and force of gravity are not the same thing, weight and force of gravity are. And I know it's a little sloppy in the language, but you just have to get used to it. So you'll hear me sometimes say an object has a force of gravity acting on it of 100 newtons, but I might also say an object weighs 100 newtons. That's the same thing. Hope you enjoyed the post lab.